In a previous unit, we discussed the operation of the steam-water cycle in a typical power plant. We looked at various steam systems and their components and discussed how they function together to improve the efficiency of the steam-water cycle. In this unit, we're going to discuss one of the important parts of a power plant steam-water cycle. We're going to look at the construction and operation of main condensers that are typically found in power plants. We'll show some examples of circulating water systems and air removal systems. We'll talk about operator checks and methods for troubleshooting problems that sometimes occur in main condensers. Finally, we'll discuss the operation of a very important plant safety system, the fire protection system. We'll begin with main condensers, their function, construction, and operation. Regardless of the design or type of condensers used in a plant, their main function is to convert the steam exhausted from turbines into condensate. The condensation process improves a plant's efficiency. Most main condensers operate at pressure less than atmospheric. This vacuum increases the overall pressure drop across the turbine and increases the useful power output of the turbine. But a condenser also has another function. That is, to remove air and non-condensable gases from the condensate. This air removal, called deaeration, decreases the oxygen concentration of the water, which in turn reduces the amount of corrosion in a condensate feedwater system and a boiler. Besides improving plant efficiency and removing air and gases from the water, the condensing of steam allows us to continuously reuse the pure water in the steam water cycle. For these reasons, condensers play a very important role in power plant operation. So, let's take a look at a typical condenser and identify its parts. This drawing shows a side view of a typical single-pass main condenser. We'll see what's meant by single pass in a few minutes. This condenser has tubes, a shell or casing, tube sheets, water boxes, several tube support plates, a hot well, deaeration trays, a steam inlet, a condensate outlet, a circulating water inlet, and a circulating water outlet. During normal operation, cool circulating water enters the condenser through the circulating water inlet. The water flows through the inlet water box and then through the tubes. At the same time, steam enters through the steam inlet and flows around the tubes. When steam comes in contact with the surface of the cool tubes, its latent heat is transferred to the circulating water flowing through the tubes. This causes two things to happen. Steam condenses on the sides of the tubes, and circulating water is heated. The heated circulating water flows through the outlet water box and into the outlet piping. The condensate drips off of the tubes and flows over the deaeration trays. Some of the steam in the condenser flows through the condensate as it drips from the trays. This removes or scrubs air and other non-condensable gases from the condensate before it flows into the hot well. From the hot well, the condensate flows out of the condensate outlet and into the condensate system. Air and non-condensable gases are removed from the condenser by the air removal system, which we'll talk about later on. That's basically what happens in a typical condenser. But before we leave this drawing, let's briefly identify some of the other condenser parts. Tube supports are plates that support and align the tubes. The tube sheets support the tubes at their ends and separate the steam in the shell from the circulating water in the water boxes. The condenser shell is a casing that forms an airtight seal around the entire condensing region. Well, we've briefly discussed how a condenser is constructed and how it operates. We used a single-pass condenser design in our drawing to illustrate the important parts involved in the condensing process and also to show you the flow paths of circulating water and steam. But another common condenser design is the two-pass design. The difference between a single-pass and a two-pass condenser is on the circulating water side. In this two-pass condenser, one of the water boxes is divided into two sections by a partition. These sections are called the inlet section and the outlet section. For this type of condenser, circulating water flows into the inlet section of this water box through one set of tubes, called the first pass tubes, and into the collection water box, located at the other end of the condenser. From this water box, the circulating water flows back through the other set of tubes, called the second pass tubes, through the outlet water box, and into the circulating water outlet piping. The steam side operation of a two-pass condenser is very similar to the single-pass design. Steam enters the steam inlet, condenses, and collects in the hot well. It is a very common design for modern main condensers because it has considerable flexibility while in operation. For example, if a leak occurs in one of the thousands of tubes, only 1/2 of the condenser needs to be shut down. To do this, we stop the circulating water flow through the tubes of the affected half. With only 1/2 of the condenser shut down, the circulating water flowing through the other half of the condenser can continue condensing steam exhausted from the turbine. This allows the turbine to continue to operate while the leak is located and repaired. Depending on the operating conditions, the turbine load may have to be reduced while 1/2 of the condenser is out of service, but the important thing to remember is that the turbine continues to operate under these circumstances. It should be noted that this 2/2 separation is strictly on the tube side of the condenser. The shell side has no such division. So, steam can flow throughout the entire shell. We'll see that a little later. If we move in a little closer, you can see the tubes more clearly. You'll notice that the tubes are arranged in sections. This arrangement leaves spaces between the tubes, called steam inlet lanes. These steam inlet lanes are important to the condensing process. When steam flows into the condenser, these lanes direct the flow of steam around all of the tubes and cause heat transfer to take place evenly throughout the condenser. In the center of the tube sections, there's a region referred to as the air exit lane. These tubes are called the air cooler section. Since these tubes are separated from the rest of the tubes in the shell, and steam does not flow directly over these tubes, this section of the condenser is relatively cool. Right now, I'm in an access hatch of the shell of this condenser. We've seen all the components we can from the outside of this condenser, but in order to get a better understanding of the internal components, we'll go inside the shell of this condenser for a closer look. Now that we're inside the condenser, let's look around and identify some of the condenser parts. Just below me are the circulating water tubes. These are the tubes that carry the water through the condenser. The exhaust steam from the turbine flows past these tubes, is cooled by the circulating water, and condenses. These are tube supports. Besides supporting the tubes in the condenser, they also keep the tubes in alignment. This allows the exhaust steam to flow past all the tubes. Up above me is the steam inlet. This is where the steam enters the condenser. This large pipe is a collection header located at the top of the air exit lane. These pipes are air offtake pipes, and they connect the collection headers at the top of the air exit lanes to the air removal system. That one connects to this header, and the one I'm sitting on connects to the header on the other side. If this condenser were in operation, there would be a vacuum pump removing air from these pipes. The vacuum pump would create a vacuum in these pipes and in the air exit lanes, making the air exit lanes the lowest pressure regions in the entire condenser. We'll discuss why that's important in a minute. You'll notice there isn't any partition in here dividing the shell side into halves. This means that steam can fill up this entire shell and flow around all the exposed tube surfaces. The area between the two major groups of tubes is called the central steam lane. The areas between the tubes and the shell are called the side steam lane. Steam enters through the steam inlet above and flows down the central steam and the side steam lane. As the steam flows around the outside of these tubes, some of the steam will flow down through each of the steam inlet lanes. It's difficult to see the flow path of steam down the steam inlet lanes from inside. Let's look at the flow path from an end view of the condenser. Even though we're looking at the tube sheet, this view will help us show the flow path of steam through the steam inlet lanes. As the steam flows through these inlet lanes and around the tubes, latent heat is removed from the steam. As we discussed earlier, the steam condenses and drips off the tubes into the deaeration trays and eventually falls into the hot well. During the condensing process, air and non-condensable gases are released from the condensate. This air continues to flow with the steam. As we noted earlier, the air exit lane is the lowest pressure area in the condenser. The steam-air mixture will flow into the air exit lane and up through the tubes in the air cooler section. The cool water in these tubes will cause nearly all the steam to condense, leaving only air at the top of the air exit lane. This minimizes steam and moisture carryover into the air removal system. The air at the top of the air exit lane collects in this pipe and is removed through the air offtake pipe. Now let's take a minute to talk about what happens in a two-pass condenser and compare its operation with the single-pass condenser. We'll use this drawing of a two-pass condenser for our discussion. We'll begin by discussing the similarities. Like the single-pass condenser, this condenser also has two identical halves on the tube side. In the middle of the tube sections, there are also air exit lanes. This upper section of tubes is the air cooler section. These lower tubes are often referred to as the vent condenser. Like the tubes in the air exit lanes of a single-pass condenser, these tubes condense the steam in the steam-air mixture flowing through the air exit lane. Between the two halves is a central steam lane. There are side steam lanes around the outside of the tubes. As we look at a section of the tubes close up, you'll notice that there are also steam inlet lanes between these tubes. That's basically the similarities between the single-pass and two-pass condenser design. The major difference is this partition. It divides each water box into an inlet section and the first-pass tubes, and unlike a single-pass condenser, an outlet section with the second-pass tubes. This design causes the circulating water to flow through the condenser twice, or in other words, make two passes through the condenser. The operation of a single-pass and two-pass condenser is very similar on the steam side. As we noted earlier, the choice of a single-pass or multi-pass condenser is based on plant design and heat removal requirements. Well, so far we've looked at a condenser's construction and the flow paths of the circulating water and steam, as well as the way air is removed from the condenser shell.